engineer from the Philippines. And together with me is my colleague, City. So she'll be my technical assistant and she'll help me in answering your questions. You may put your questions on the chat box or you may ask them at the end of the presentation. So we'll allot enough time to cater your questions. All right. So again, this is a webinar good for an hour about signal analysis with machine learning using MATLAB. So this webinar is presented to you by Texas Computing Solutions and Ascenda Systems. And yeah, let's start. Okay, again, so friendly reminder, please mute your mic and turn off your webcam to avoid distractions to the presenter and to the other attendees. All right, so with any presentation that I am doing, I actually start with some sort of a demo, right? So I start with the finished product. So what we're actually gonna do is we're gonna classify normal or abnormal vibration data from turbines, right? So the significance of it is one, if you're a site engineer, you can actually use it for predictive maintenance. Now we have like three types of maintenance, right? So we have the reactive, preventive, and predictive maintenance. So reactive maintenance means that you will do the maintenance after the failure happens, right? So it's kind of costly because there will be downtimes in your plant or your system. And on the other hand, you have the preventive maintenance, which is fairly common in automobile, right? So maybe you would like to do preventive maintenance for the next 60,000 kilometers or so, but it's kind of costly because you're not actually getting the most out of your system, right? Maybe you are doing the maintenance prematurely, right? So the best way to do the maintenance is to do the predictive maintenance, right? So predictive maintenance balances both the premature and the late maintenance, right? So it's less costly and it's very beneficial to your system. Okay, so as I mentioned, this will be like beneficial to the site engineer to determine if your plant or turbine needs maintenance because maybe one of your part or bearing is failing. Okay, so this is divided into two parts actually. So first we will discuss the signal processing and signal analysis. Then we'll then proceed with the machine learning proper. So we will discuss some of the fundamentals of machine learning to help you understand the theories behind it, right? So we'll start with the definition of signals. I'll give some examples, some signal processing techniques, and we'll go ahead, extract features from our signals. As you know, machine learning requires manual feature extraction, right? Unlike deep learning. So deep learning actually has the capability to extract your features automatically using a single network. But that's not the case with machine learning. So we have to find the means to extract the features from your signal. And what's good about this is that MATLAB has several toolbox that can help us extract our features from our signals or images or any other data. Okay, so machine learning, then subsets like supervised learning, unsupervised learning, then some applications in the real world, and finally we'll have our demo of signal classification using machine learning. Okay. Okay, so first let's define signal or signals per se. So basically signal is just any physical quantity that carries or conveys information, and it can be a quantity that varies with respect to time, space, or frequency, right? So as you can see here in this demographic, we have a heartbeat, right? So it varies with respect to time, maybe a few milliseconds between the peaks or troughs. And actually heartbeat is one type of a signal, right? So it conveys some information about the patient's well-being, right? So if you have fast heartbeat, then maybe you are doing some cardio or other type of activities that can spike your heartbeat, right? So it conveys information. So signal comes in all forms, right? You can have hand signals or electrical signals or audio signals, right? Oh, sorry. There's some chats here. Can anyone see my screen? The screen that I'm showing right now? Signals. Fine here. Okay. Okay. Thank you for answering. Yeah, I don't know why is that. Okay, it's good. And can you hear my voice clear or there are some distortions? Okay, clear, clear. Right, right. Thank you. Yeah, so let me just continue. So we have here signals, right? So here are some examples of signals. So first we have EEG signals, right? So you can use EEG signals to somehow predict whether a patient will have seizure from epilepsy or not, right? And another type of signal that is fairly common in our industry is from seismographs, right? So seismologists use these signals to detect earthquake activity, right? So they can detect the magnitude or the intensity of the earthquake. And finally, we have here a chart for a cryptocurrency called Bitcoin. So actually, this is my favorite application of signals, right? So it's on finance. So it actually tells us that there are lots of tools that you can use for cryptocurrency to determine buying or selling signals, right? So in this case, we have here one tool called MACD or Moving Average Convergence Divergence. So you can use it to guide you in your buying or selling trading, right? And there are lots of types of signals everywhere. Now, moving on to the signal processing, it's just like a set of methodologies or tools that helps you analyze or process your signals and also extract your features, which I will show you later on. So it can be uniformly or non-uniformly signals, periodic or aperiodic. Okay, so it can have a time invariant or also discrete time signals, something like that. Also, you have here the filter design. Let's say you want to design a low-pass filter to just separate the low frequency from your signal, right? And you can have resampling, smoothing. So smoothing, I think one example is like for auto-tuning. I don't know, like when the singer's voice is awful, right? So you can use auto-tuning to correct the pitch, whether it is sharp or flat, right? So you can use those signal processing techniques and so on and so forth. Yeah, loud and clear. Thank you, thank you. Okay, so spectral analysis is just like the opposite of time domain analysis. So spectral means somehow deals with frequency, right? So instead of plotting our signal with respect to time, we're plotting our signal or our quantity that we're studying with respect to frequency. So that's spectral analysis for you, right? So one common tool or mathematical methodology that you can use is applying Fourier transform, right? So Fourier transform basically just converts your time domain signal into frequency domain signal. So you can see the formula here on the right. And actually, we won't require you to memorize this formula because MATLAB supports applying the FFT or Fourier function transform easily, right? And if you're an engineering student, maybe you have come across this meme before. So this just compares the Fourier transformation and your Fourier transformation in your college. So actually, I can't relate in this because I took 6 years to finish college, right? So it's more like 6-year transformation. Anyway, so let's proceed to our first demo, signal processing. Let's switch to our MATLAB screen. Okay, so I have here a short demo that demonstrates or shows you how you can leverage signal processing techniques to make sense out of your data. Okay, now one of the most common steps that you can use or you can do in analyzing your data is to visualize it, right? Because we are visual learners as humans. So first, let's load our data and plot it. So actually, our data is the sunspot data. So what we're trying to determine here is the cycle of sunspot activity on Earth, right? So here we have here a line chart, right? So it shows the trend. So it depends on you on what type of chart or graph that you will use. But if you're after looking for trends, so line chart would be the best chart to go, right? And for patterns, you can use scatter plots. And for distributions, you can use histograms or density plots, right? So we have here the plot of, how's it? Year, I guess this is year. Yes, so it's year. Annotate your content. What is this? Oh, sorry. Anyway, so it's sunspot data. But you can see my screen, right? The MATLAB screen. Anyone? You may type on your chat box. Okay, cool. Thank you, thank you. Okay, so we have here the sunspot data. So we plot year with respect to the Zurich number. So Zurich number is just the fancy way of measuring how many sunspots are there in a particular region of the sun, right? So it's pulsating, right? So it's not really constant. But the problem here is that we can't get much information here yet, right? So it's not very intuitive. So we can apply some signal processing techniques. Maybe we could zoom in. So first we have plotted from 1700 to year 2000, right? So maybe we can plot the first 50 years only. So here it is. So it's like the zoomed in version of our previous plot. And again, it's not very intuitive. Yes, you can see the trends, but it doesn't give much information to us, right? So let's go ahead and dig deeper. So maybe we could use Fourier transform this time, right? So let's try that. So plotting the Fourier coefficients, the real part and the imaginary part. Well, actually, Fourier coefficients is not that intuitive, but it will be useful if you're trying to construct your signals, right? But in this case, using them in a plot, so doesn't give much, and it's actually a bit confusing. So what you can do is we can measure its power, right? So how do we measure the power? So we just find the magnitude of your coefficients, then square them. Okay, so that's what this part of the script is doing. So let's try to plot power with respect to frequency. So again, I have mentioned to you that you don't have to memorize the formula for Fourier transform, right? Because you can see here, we actually have the FFT function that you can easily call, right? So no need for memorization. Okay, so we have here the plot of cycles per year, which is actually a measure of frequency, because again, frequency is just measuring the occurrence or the cycles per period of time, right? With respect to power. So what it tells us is that sunspot activity peaks more or less than once in a year, right? So it's actually peaking at 0.1 cycles per year. Now, if you want to determine how long or what's the period between the sunspot peaks, right? So we can actually invert our x-axis variable into year per cycle. So it's a measure of time now, right? So that's what we're gonna do here. Sorry. Okay, where's that? Okay, here. Let's run that script. And you can see here, finally, we have here the plot of years over cycle with respect to power. So what it tells us is that sunspot activity peaks at around 11 years, right? So if you try to open a web browser and search for the sunspot activity period, you can see that it peaks on 11 years, right? So that's one way to put it. Okay? Yeah, so going back to our presentation here, let's see. Let me just, just proceed. Okay, so we're now on the feature extraction part. So I think this is one of the most important part with machine learning workflow, aside from the processing and cleaning of your data, because most of the time our data is dirty, right, or unstructured. So I think feature extraction comes at par with the importance. Okay, so without the right features, you can't expect a good model. So I want you to remember this, that your model is only as good as your features. Okay, so if you have poor features, you will have poor models. Okay, so basically garbage in, then garbage out. So that's the mantra of machine learning. Okay, so again, this is just a process of transforming your raw data into numerical features to feed into your model. So this will serve as your input to your machine learning algorithms or models. Okay. Now, feature extraction can be done manually and automatically. So for the case of machine learning, you have to do it manually. But for deep learning, you can use deep networks or convolutional neural networks to extract those features automatically, as in the case of image classification. So I have here an example. So we have the raw data, and for every layer in the neural network, you can extract features, right? So it can be low-level features such as edges or the color, can be blobs, or the mid-level features such as the facial parts of the humans, or the high-level features, okay? So that's distinguishing features of those faces, okay? And you can use those features to determine whether the image is an image of a woman or a man, okay? So that's one way to put it. So again, the biggest challenge here in machine learning is finding the right feature. So having the wrong feature will lead to poor performance. Okay, so sometimes it is hard to disambiguate between the features. So for instance, you have here the features for damage case and undamaged case, right? So you can see here that they have similar histogram or distribution, right? So it's kind of hard to determine the significance because they may come from the same distribution, right? So there are no significant difference between them. And also, if you will try to plot it using spectral estimation, you can see the trend of the signal. There is little to no difference, right? So it's kind of hard to just use these features for your machine learning model because your machine will have hard time in distinguishing the damaged and undamaged case. Okay. Okay, so we're now done with the signal processing and the feature extraction part. So we'll now proceed to discuss some of the machine learning fundamentals. Okay, so machine learning basically, how do I put it? So you're actually trying to transfer your knowledge or your knowledge or know-how into the machine or the device. Okay, so machine is any type of device where you can embed your algorithms or your models. Okay, it can be your mobile phone, it can be a Raspberry Pi, a microcontroller, or it can be a powerful computer. Okay, so we're trying to teach the computers what comes naturally to us, which is learning from experience and learning from data. Okay, so one example is like teaching a kid to distinguish the types of animals using a flashcard or a visual props, right? So you can put some images in front of the kid like dogs, cats, or rats, and eventually they will learn to distinguish the types of animals, right? So we want to transfer that knowledge to a machine. And actually, we have several types of applications for machine learning. It can be applied in finance, right? So, for instance, you would like to predict the price for a particular region or particular country, right? So you can use machine learning for that. Then, if you would like to detect the facial features or face recognition, you can use machine learning. For biology, you can use machine learning too, and for energy here. So this is one of the most common application of machine learning, which is load forecasting and price forecasting, right? And you can also use it in robotics. So particularly, you can use reinforcement learning to make your robot learn from its environment, like Boston Dynamics, if you're familiar with that, right? So they're using reinforcement learning to help their robotic dog learn from the environment to do some tricks like walking, jumping, and other types, right? And finally, you can have machine learning on NLP or natural language processing. So what's good about machine learning is that if you don't know the equation or the underlying model of your plant, then you can use machine learning to still do the predictive task, right? So because sometimes it is hard to accurately model your plant, right? So there can be some random parameters or there can be some parasitics, right? So working before in a electronics manufacturing company, sorry about that. So we tend to try to model our system, right? So like the power supply system, and it's kind of hard actually because there are lots of parasitics there. So we can actually model it accurately and close enough to the reality. So what you can do is that if you have lots of data, you can try to apply machine learning for that. Okay. So now we have several types for machine learning. Okay. So we have first the supervised learning. So supervised learning is the type of machine learning that you usually see for predictive models. Okay, so whether you're predicting the temperature, predicting prices, or predicting the type of animal present in an image, that's supervised learning. So basically, supervised learning needs your data to have both input and output. So it's basically saying that you need to have the input or the features and your output data. So output data is like the correct answer, right? And what else? So under supervised learning, we have here several classifications. So we have regression and classification. So the only difference between the two is that regression deals with continuous or numerical data. Okay, if it's price, temperature, and on the other hand, you have classification, right? So classification deals with categorical and discrete data. Okay, so it can be how's it activity like walking, running, or other types of activity like um, laying down. So we have here actually an example. So classification tasks to classify human activity from your sensor data using the accelerometer or gyroscope, so that you can determine whether a person is walking upstairs, sitting, just standing, or laying down. Okay. Now, another type of machine learning or its subset is unsupervised learning. And unsupervised learning, unlike supervised learning, only needs input data. Okay, so you don't need the output data. Now, you might wonder, okay, what task can we do with unsupervised learning if we only have input data? So what you can do is do clustering, right? So you can discover the internal representation of your data, find patterns, and so on and so forth. Okay, so we have here the example of clustering your data according to the gears of your vehicles, right? So first gear, second gear, and so on and so forth. And we're plotting it as engine speed with respect to the vehicle speed. Okay. And finally, we have here the machine learning workflow. So I think this applies to most of the data science workflow, right? So we need to find the means to access and load our data, whether it is from a repository, from a server, or from your sensors. Then you need to preprocess the data. So you need to preprocess your data if it's unclean or unstructured, if it has outliers, duplicates, or other types of impurities. Okay. Then after cleaning your data, you need to derive the features. So this is only true for machine learning. Okay. So you need to derive the features manually from your preprocessed data prior to training your models. Okay. So after you have trained your models, you can evaluate it. So find the best model for your data set or for your problem, then evaluate it using some evaluation metrics such as accuracy, root mean squared error, or R squared, and so on and so forth. Okay? Then finally, you would want to integrate it to a production system, whether it is mobile or laptop or any other type of end device. Okay? So these are some of the common models for machine learning in MATLAB. So you have supervised learning and unsupervised learning. Now, I want to tell you that there is no one machine learning model that fits all of the problem. Okay, so it depends on your use case and on your problem. Okay, there are some models that performs well in this data set, but when you try to transfer that model into a different data set, whether if they are the same problem like regression, they won't perform very well. Okay, so it's different for every use case. But if you will ask me what's the most versatile machine learning model out there, I would say neural networks. So why? Because neural networks can be used for classification, you can use it for regression, and finally, you can use it for unsupervised learning or clustering. Okay, so it's very versatile because you can easily control the complexity or simplicity of neural networks. Okay, so neural networks is actually discussed in detail for a deep learning workshop. Okay. All right, so we're now in our demo for machine learning. So let me switch again to my MATLAB screen. Okay, let me just clear my variables here. Okay, so actually it is a good practice to always clear your workspace before starting a new project. Okay, so to prevent confusion or variable confusion, right? Okay, I don't know how to put it, but yeah, you have to clear your workspace. Alright. Okay, and all right, so let's start with the demo. So again, this is what I've shown you in the start of our presentation. So we need to classify normal and abnormal vibration data, right? So again, the first step here is to load your data. So it's actually showing here the same workflow that I've shown you for machine learning. So access, explore, preprocess, then develop your models, then integrate it, right? So it's just telling us that MATLAB can do everything or the entire workflow, right? So without even changing platform, you can do everything with MATLAB here. Okay, so let's first load our data, then assign them to two variables. So vibe1 is actually the normal data and vibe2 is our abnormal data. So if you would like to explore your data, you can double click your variables here in the workspace. So let's say double click the sample data. So what's good about this is that the data is already labeled, right? So we have here the output already. So we have the normal and the abnormal classes. And we have here the vibration data. So double clicking it will lead you to the time with respect to the magnitude of vibration. And if you will plot this as a line graph, you will see the exact plot such as this one. Okay, so let's plot that running. So this is what you will see. And you can actually pan or move it, or you can actually zoom in or zoom out, okay, in your data. So that's about it. And actually, this doesn't tell us much right now, but later on, we will extract its features to make our data confess, right? So that's how I put it. We're actually making our data confess by extracting their features prior to modeling. Okay, you might want to preprocess your data. So using the signal analyzer app just to explore it. So one thing that you can do with your machine learning workflow is to do EDA or exploratory data analysis to see some trends or correlations and associations. Okay, so let's just wait for this to load. Okay. Yeah, so there we go. Let's separate them. Okay, so we have here the normal and we have here the abnormal signal, right? And what you can do here in the signal analyzer app is that you can use spectrum analysis, right? So you can view the spectrum of your signal over here. And I think we can separate them again. Like that. And actually, you can also use other techniques to analyze your signals here. So I won't dig deeper much here, but what I'm trying to show you here is that using the spectral analysis doesn't give us much information about our signal, right? So you can see here the signal doesn't have much difference. So it's actually shown here. Let's see. There we go. So there's no or little to no difference with our normal and abnormal signal over here, right? So what you can do now here is to extract the features. So let's get into business. And what you can do here is call the diagnostic feature designer. So you can either type it here in the apps ribbon, or you can type it in your command window. So diagnostic feature designer over here. Click enter. It will open another window. Then what you can do is import data. So let's import our sample data. So remember, our sample data is the data that we uploaded in the previous tab, right? So you can click next, next. Let's call that what? Sample. Okay, so now it's loaded, and you can see here on the ribbon top, you have the computational options. If you have the parallel computing toolbox, then you can click here use parallel computing to speed up the feature generation. Then if you would like to process your signal, you can find here filtering, residue generation, or spectral estimation, right? And for the feature generation, you can use here time domain features or spectral or frequency features. Okay, so let's start with time domain features here. So this is just a demo to show you how to extract your time domain features from your signals. So let's just wait for that. So the speed of the feature generation actually depends on the specs of your device, okay? So I think it's busy. Let's wait for it. Yeah, so for the meantime, I think I can check the questions here. Okay. Let's check again. So I think my computer is hanging. Okay, now it's processing. Yeah, actually, if MATLAB crashes, normally there's a, how's it, BC something. There's a BC prompt here on the lower right. Or you can actually refer to this progress bar on your lower right. Okay. Okay, so there we go. We have here the features now. We're extracting again. Sorry about that. So we have here THD, total harmonic distortion, the standard deviation. So these are like statistical features, right? The skewness, signal to noise ratio plus distortion, peak value, and the mean, RMS, and so on and so forth, right? Right now, we only have the time domain features. So what if you want to create the spectral features? So first you must do spectral estimation, right? So because, let me just show you. If you click spectral features right away, an error dialog will show up, right? So you can see here that there will be a prompt that tells you to do spectral estimation first. So that's what we're going to do. Spectral estimation. Okay, let's wait for it. There we go. We're having progress. Okay, so now we have a spectral model here. So we can now proceed to extract the spectral features. Okay, so click OK. It's now extracting our features. So again, it's in progress, right? Okay, it's done now. So previously we only have the time domain features, right? So now we have several more features. So we have the band power, peak frequency, and some other features that are common to both domain analysis, right? So what you can do from here is you can opt to rank your features, because having too many features will lead to overfitting your data, right? So we don't want to use too many features that it fails to generalize over several data sets, right? So you can rank features here. So rank feature table 1. Let's just wait for the results. Okay, so it's ranking our features. Actually, there are lots of ranking feature algorithm, and you can use machine learning models to do it too. Like you can use random forest or extra extra trees regressor to rank your features. But it's actually not covered in this webinar, but just saying, you know. So it ranked our features using t-test over here. So our most important feature here is the shape factor, followed by the clearance factor, right? What if you want to perform a different test to rank your features? So you can find it here, classification ranking. And if you have two classes, like in our case, we have abnormal and normal classes only, right? So we have two classes. So you can use t-test, entropy, ROC. I don't know how to pronounce this, so I skip it. So if you have multiple classes, like say more than two classes, you can use one-way ANOVA or Kruskal-Wallis test. Okay, so let's just try to click this one. And what happens? Okay, sorry, apply. So when you select a feature importance algorithm, don't forget to click apply, okay? So you can see the difference with the t-test in Wilcox-Scott, right? So you can see here the most important feature for Wilcoxon is the mean, right? And the skewness. Right, so I think that's about it. And if you would like to export your feature table, you can click here, export, and generate the function features, or export your feature variable into your MATLAB workspace, okay? But now, I'm not gonna do that because we already have a prepared feature here. So we have here the feature table. So I'm just gonna load this one. But you can try that on your own, right? So on home, try to experiment with the features. So once we have now the features, we can create our model. Okay, so our classifier. So with every machine learning model, you will often find that you are splitting your data set, right? So splitting it into training and testing data sets. So what's the purpose of that? Okay, so basically, let me show you here a demographic. So whenever I'm discussing machine learning, I always start with the most simple model, so which is linear regression. Okay, so basically training here means that, so let me type it. Training means estimating the parameters of your model. Okay, and testing, on the other hand, means evaluating your model. Okay, so that's the difference here. So basically, training is like trying to teach the kid on how to classify it. Then testing is like examining him or her in classifying images of animals or other types of images, right? So we have here the equation for a simple line, y equals mx plus b, where m is the slope and y is the, or b is the y-intercept, right? So basically, m and b here are the parameters that are estimated during our training. Okay, so if I try to fit a line here, so our objective here is to fit a line that has that goes over most of our data points, okay, with minimal distance or minimal residue or residuals. Okay, so how do we do that? So we could actually change our slope. So changing the slope will change the inclination of your line, right? And changing the y-intercept will change its position, right? So you can use these two parameters, m and b, to find the best fit line to your data set. Okay, so that's actually what training actually means in machine learning lingo. Now, if you have find the best line here, you can now test your model or your line, whether it is to your liking, or whether if it if it meets your expectations, whether it has low error and good R-squared value, something like that. Okay, so that's basically the difference between training and testing. And most of the time, training set is greater than testing set. Okay, so you can see some ratios like 70 is to 30, 80 is to 20, or 75 is to 25. Okay, those are the most common ratios. So if you will ask me what ratio to use, so if you're dealing with small data, it will be good to use most of your training into, or most of your data set into training. So you might opt to use 85-15 or 80-20 ratio. Okay? Because you have this small data set, so you need to estimate the parameters correctly as much with as much data as possible. Okay? But if you have data, you can use other ratios. Okay? So it doesn't really matter much. Okay, so that's the purpose of this, split the data. So now we have here the training data and the testing data. Okay. Now, creating your model comes in two ways. You can create it from scratch, like coding everything, or you can use a interactive type modeling. So we have here the classification learner app that lets you to develop your machine learning models interactively, or it's like a GUI type of modeling. Okay. So let's just wait for that to load. Okay, so once you're on the classification learner, you can click new session, then select your training dataset. Okay. So again, you will see here the features that you can use. You may tick them off if you find it unnecessary. So selecting the features actually requires domain knowledge. Okay, so it's up to you whether you think based from your domain expertise that a particular feature is needed or not. Okay. And finally, you can see here on the right, we have validation. Okay, so validation is very important to detect or prevent overfitting. Okay, so without validation, you don't have protection against overfitting. So by the way, what's overfitting, right? So maybe we can show this demographic here first. So we have here the bias or variance trade-off, which shows you that if your model is too complex here, so this is like the optimal capacitor complexity of your model. So if your model is too complex for your problem, it leads to overfitting the data. Okay, so overfitting only means that your data performs well during training, but it performs poorly during testing or on other data set. Okay, so again, let me try to put it here. So overfitting is failing to generalize on multiple data sets. Okay, so maybe your training accuracy here, training accuracy is 90%. Then your testing accuracy is only 50%. Okay, so that's like overfitting because you're performing well in training but poorly on testing. Okay, so that's overfitting. And underfitting on the other hand, so pwede ko na rin siguro lagay dito. Let me put it here. Underfitting. Let's put it here. Underfitting. Failure to capture the true relationship. Okay? So basically with machine learning kasi, we are trying to map our input, which is X, to our output Y, right? So underfitting is the failure to capture the true relationship between your input and your output. So if you have training accuracy of, let's say, only 60%, so that's a good indication that your model is underfitting your data. Okay? So don't even bother doing the testing because you will expect worse, right? So it can be 60%, 50%, or something like that. Okay? So basically, if your model performs poorly on training, that's underfitting your data. Okay? So meaning underfitting happens if your model lacks the complexity, okay, or if it's too simple for your problem. Okay? Now, you don't want to make your model too complex that it will overfit. So you're finding actually the sweet spot between the bias and the variance. Okay? So bias is like the assumptions that your model is making. So like linear regression, there are lots of assumptions that linear regression makes. For example, linear regression assumes that your data is linear or linear in nature, right? And variance is like the variation or difference between the performance of your model over different data sets. Okay, so that's about it. So going back, classification learner. So okay, now cross validation here is just making your model test on different data sets or multiple data sets. Unlike here, holdout, if you choose holdout, you will only test your model on one set of training or one set of testing data set only. Okay. But if you choose cross-validation, it will train your model multiple times on different testing and training data, such as this one in this demographic. Okay, so in the first iteration, we have here the training data. This is your training data. This is your testing data. Okay, so we estimate the parameters using this and evaluate your model using this data set. Then for the second iteration, this is your testing data and the rest is your training data, and so on and so forth. Okay, so that's validation for you. Okay, so start session. Let's see. Okay, I think we're running out of time, so we have to speed up a bit. Sorry about that. Okay, so we have here some options, right? So again, you can use parallel training to speed up your training. And you can see here several models that you can use for classification. You have here support vector machines, naive-based classifiers, KNN, and ensemble classifiers. So you can also train everything, right? So what's good about this is that with machine learning, we don't know what's the best model until we try them, right? For our dataset or our problem. So what's good about MATLAB is that it lets you train your model all at once. So you can train everything here or just train every quick to train models here. So let's just opt for that, then click train. Okay. And you can see here it's training 4 at a time, right? So because I have like 4 parallel workers. If you don't use parallel working, it will train 1 at a time. So it's kind of slow. Okay. Okay, so it's now done. You can see here the best performing model for our problem, which is the KNN. It has an accuracy of 96%. So here are some of the parameters and hyperparameters used of our model. Then for the performance, you can use the confusion matrix. Okay. So confusion matrix is not meant to confuse you. Okay. So it's actually a measure, visually a measure of how confused the model is in classifying the correct classes. So one way to explain confusion matrix is look at the numbers here. So, or the diagonals. So the blue diagonals represent the correct classification, and the what's this? Flesh diagonal, flesh colored diagonal represents the misclassifications. Okay. So first, let's examine 79. Okay. So what does 79 means here? So it means that 79 of your data is truly or actually abnormal, and your model predicted it as abnormal. So that's correct classification, right? On the other hand, we have here 89 data points that are actually normal, and your model classified it as normal. So it's correct classification again. So on the other hand, we have here 5. So you have 5 data points that are truly abnormal, but your model classified it as abnormal. So that's a misclassification because the actual class is abnormal, but your model predicted it as normal. And same goes with this, you have 2 data points that are normal, but your model predicted it as abnormal. Okay, so that's confusion matrix for you. And if you would like to view the normalized scores here, you can click here true positive rates and false negative rates. So it's just taking the correct classification versus the misclassification row-wise, and it must sum to 100%, right? And column-wise, you can use this false positive rate or false discovery rates, okay? So it calculates your scores column-wise here, okay? And actually, what's good about this is that you can export this figure and you can put it eventually in your research paper, in your thesis, or other publications, okay? So another measure of performance of your model visually is to use ROC AUC curve, okay? So AUC basically means just area under the curve, okay? So a perfect classifier has a area under the curve equal to 1. So how is that? Because you can see here the false positive rate and the true positive rate on your axis, right? So basically we want 0 false positive rate and perfect true positive rate or 1, right? So ideally this red dot here must be placed here, correct? Right? So that's the perfect classifier. But since our classifier has imperfections or some misclassifications, hence the result here, okay? So area under the curve is 0.96. But the closer to 1, the better the classifier is, okay? So you can now generate the function for this for every training steps that we have done. So you can see here the train classifier, which you can easily call as a function, right? So this is a function. So you can see here the parameters used by the model and other informations that you may wish to use. Okay. And finally, you can also export the model here. So export model and save it to our workspace. So clicking OK. Let's see the window. Okay. So you can see here in our workspace, we have a new variable called trained model. So it describes everything about our model that has been trained. Okay. So now we have the model that has been trained. We can now test. We can now test its performance. Okay. So we're just calling the classifier here in our model. Then use that predict function to predict to do prediction on our testing dataset. Okay. To evaluate its performance. So you can see here the percentage scores, meaning 94% are classified as normal and the model predicted it as normal. Okay. So the only difference with this and the previous confusion matrix that this is in terms of percentage. Okay. You can see here there's a fairly good amount of misclassifications happening here, right? And I think that's about it. And the rest of the section just deals with predictive model optimization. Okay, so if you're not happy with the performance of your trained model, you can opt to optimize its hyperparameters, tweak it, and maybe do other types of methods. Maybe if your model is overfitting, you can use regularization, or maybe you can use dropout if you're using neural network, something like that. And those techniques are actually discussed in our deep learning workshop. Okay. So again, I'm sorry for the lack of time to discuss everything about machine learning because it's a very broad field, right? So there's so much to talk about machine learning. So hyperparameter tuning. What else? Okay. And finally, you can actually integrate it with your system, right? So we have here the trained model that has been exported. Then what you can do here is you can convert your MATLAB code into C code over here. So that you can, so the purpose of converting your MATLAB to C code is that if you will want to embed it to a microcontroller, right? Or any powerful processor, you need at least C code or C++ or maybe assembly code, right? So again, let's try to test the performance of our model. Oh, what happened there? Index. Oh, sorry. Wait a minute. Yeah, so basically, this just deals with testing our model on the testing dataset, which we actually seen before, right? So we actually test our model on the testing dataset to generate the confusion matrix. So this is just another way of showing how to test your model by using the control buttons. Like you can use the numeric slider to scroll up and down within your testing dataset. Okay, so I think that's about it. And what else? So going back to our presentation. Okay, so we have here the key takeaways. So again, we have shown that signal analysis and processing can be easily done with MATLAB, and you can extract the features using the diagnostic feature app designer. And you can train, create, use machine learning models with little to no coding using MATLAB. And you can actually convert your MATLAB code to C code for your applications, right? And again, this webinar is presented to you by TechSource and Ascenda Systems. So we are the sole distributor of MATLAB and Simulink products in the ASEAN region. We're also a authorized training provider of Xilinx. So if you're into FPGAs and Xilinx products or Xilinx tools, you can contact us for trainings. And as you may have noticed, this webinar is more of a high-level discussion about machine learning and signal analysis, right? So what we have for you is we prepared a comprehensive and in-depth course about machine learning to discuss the details and the advanced topics about those two topics that we have discussed, right? So first we can go with programming and language syllabus. So this will help you develop your knowledge in scripting and doing some processing and visualization from your data. So as you have seen, data visualization is very important. And actually, in some corporations, the final step of their data science workflow is visualizing their results and showing it to their stakeholders or their clients, right? So visualization is very important here. So for the course 2, we have here the data analysis and feature extraction, which is equally important, right? So without the features, you don't have to, you can't do machine learning, right? So we have here the signal processing, feature extraction, image processing. And when you're dealing with images, you can use computer vision techniques or statistical methods too, okay? And finally, we have here the machine learning syllabus, okay? So again, this is a comprehensive syllabus for machine learning. So it discusses more of the advanced topics of machine learning. So more than what we have discussed so far, okay? And it also tackles some of the deep learning concepts, right? Because as you know, deep learning is just a subset of machine learning, right? But deep learning only deals with neural networks. And finally, you can go and take this course about data analytics, modeling, and machine learning with MATLAB. Okay? And I am inviting you to our future events and trainings. So you may see our events using the link provided here or the website provided here, www.techsource.asia.com/events. So this event is just the first of our many events to come during the 2020 or 2021 rather, sorry. Okay, so I am the first presenter for this year, and there are more webinars coming up that are going to be presented by my colleagues. Okay, and what else? We also provide consultancy and training services to help you in your MathWorks journey. Okay, so MathWorks basically helps you improve your workflows and maybe increase revenue for your company. And if you're a student, you can use MathWorks product to help you with your research or thesis, right? So for support, if you're already a MathWorks user, you can contact our support at techsource.asia.com. And if you have questions, I'm open to answer them now. And finally, please answer the QR code right after this webinar. Okay. So thank you very much for attending and have a good day. I'm open to questions now.